The final test of goodness of fit uses a discrete response variable rather than a continuous response variable. So we want to know if the group memberships that we're observing match the group memberships that we expect. Each individual or item that we're observing in our sample that gets classified into a group. Color, shape, might be what kind of iPhone they use, it might be whether they use an iPhone or not. But it's a discrete variable. It's a category or a group membership. But we still need to use numbers somehow. So what we'll do is we'll count how many times each group appeared. So even though the unit of observation is the individual, when we're doing our number crunching, what we're going to have for each row in our tables is the number of times is each group and how often each group appeared. And this is called a chi-squared test of goodness of fit because we're looking to see if the observed frequencies fit the expected frequencies. So here we'll use an example of a shoe manufacturer. And let's say right now in the status quo, the factory makes equal amounts of blue, red, and black shoes. They want to make sure that their production is actually matching demand. And so they are going to compare the amount sold, which are the observations, to the amount made, our expectations. So since there's three categories, we only have 2 degrees of freedom. And again, we're going to use 0.05. So that means the critical value, the chi-squared value that we're going to detect, that would say that our observations are far enough from our expectations to say that the amount sold does not match what's being produced. We will call that's going to be 5.99. So notice that it doesn't matter how many shoes we look at. We already know what our critical value is just because we have 3 kinds of shoes and an alpha value of 0.05. So what if we do a pilot study, and in that pilot study there are 3 blue, 2 red, and 4 black shoes sold at our trial store. So we will want to see if this proportion of shoes is significantly different from this expectation. So our expected proportions are 1/3 each. So we multiply it by how many shoes we saw, and since there were 9 shoes, that's 3 each. So that's our expectation. Now one thing that's important to know is that the expectation doesn't have to be a whole number. If we sold 10 pairs, then the expectation here would be 3 1/3, 3 1/3, 3 1/3. That's okay. Our observed sales do have to be whole numbers though, right? Because we're looking at counting how many individuals happen. So we've got 3 blue, 2 red, and 4 black. Notice that these totals are equal. So if we were just looking at the observed minus the expected, this one is meeting our observations. This one's a little light, and this one's a little extra, and those cancel each other out. These, by definition, always have to sum to 0. So that's not going to help us do our computations because summing to 0 is not useful. But if we square them, then the negatives go away, and we can add things up, and we're guaranteed to get some kind of positive number. And so our total here is 2. So that's why it's called chi-squared, is because it's the squared distance, sort of. But we want to scale how big the departure is by our expecteds. So we take this 1 and we divide it by our expected, and so it's 1/3 plus 1/3. So this 2/3, this is what's going to let us compare it to the chi-square distribution. You can think of this one as being sensitive to sample size, and this one not being sensitive to sample size. So our chi-squared score is 2/3, which is like 0.67. It's much less than our critical value of 5.99, so there's not enough evidence to support the idea that consumers' preferences are different for production. So we would not reject the null. We would keep on manufacturing 1/3 of each kind of color. But we did see that there's a disparity between blue and red. So what if we increase our sample size? So we'll do a follow-up study. And this time we look at 90 shoes. So here, And we get the same. So here the result, since we multiply our sample size by 10, our expecteds multiply by 10 in each category. And if our observed follow exactly the same proportions, so we got 30 blue, 20 red, and 40 black, then our observed minus expected squareds are much bigger. And our chi-squared values, which are here, these are the chi-squared values of each. So that's the chi-squared value for blue, chi-squared value for red, chi-squared value for black, and then the total chi-squared is 20 over 3, which is 6.67. That's greater than our critical value, so we should reject the null hypothesis. Consumers do not appear to be wanting shoes in equal quantities of blue, red, and black. There seem to be more black wanted and fewer red. So our p-value here is 0.036. So if we're looking at a randomly generated chi-squared value with 2 degrees of freedom, we expect to see this number only about 36 times out of 1,000. And this x squared here, that's the chi-squared. That's telling us what test we did. And the subset here, too, that's telling us the parameters are involved in generating our distribution. And there's the test statistic, and a comma, and a p. And that's sort of the standard way we report these sorts of things. So that's how you do a chi-square test. And we will spend more time tomorrow, or today probably, because you're not going to look at it until today, looking at this test with M&Ms. Oh wait, no. The summary is 9 pairs of shoes aren't enough, but with 90 pairs we can say yes. Consumers, we can say no, shoe sales don't match production. They should make more black and fewer red shoes. And that's the kind of way that this actually could be useful for you in the real life.